Great. Yeah, thanks very much, Larry, for chairing the session, and to the organizers for inviting me, and for all of you for being here. This is joint work with Alex Frankel, and in case you don't know him, there he is. I don't think he's at the conference at this point. Alex is at Chicago booth, and this work of ours is basically following up on an agenda that we have that is trying to understand sort of how allocation decisions should be made in the presence of strategic manipulation of the data that the allocations are based upon. Okay, so can everyone see my screen okay? Maybe Larry, if you could just indicate, yes, okay, good. So we're thinking about problems in which there's a designer, could be a firm, could be a government, could be other kinds of entities, that is using data that about an agent in order to assign the agent an allocation. And crucially, the data that the agent produces is under the control of the agent, at least to some extent, okay? And we're thinking about problems in which the designer wants to give, in a certain sense, higher types of the agent, higher allocations, okay? And of course, I will make that precise. So, for example, think about Amazon, who sees product reviews that are submitted about products, and determines which products to highlight in various ways. For example, which ones to return in a particular order to a search query. Okay. So, given some kind of an allocation rule that Amazon uses, sellers can manipulate the data that's available to Amazon in order to improve their allocation, say, to be higher in the search ordering results. And in particular, of course, the example that's very frequently discussed is that firms can use fake positive reviews in order to do that. So the crucial observation is that once the agent is manipulating the data that the designer has access to, the manipulation is actually going to change the inference that the designer has about the agent's type, okay, from the existing data that the designer sees. So, in general, sort of one could think about this dynamic where there's an allocation rule or a policy in place that affects the kind of manipulation that the agent engages in. The manipulation affects the inference of the type about the agent from the observable, and that in turn could affect the optimal allocation rule that the designer wants to use. And there are two natural things that once you recognize this dynamic that one might be interested in thinking about. One of them is a fixed point policy. So this is going to be an allocation rule that in a certain sense is a best response to itself, right, or a Nash equilibrium. And the crucial point about a fixed point policy is that the rule is going to be optimal in an ex post sense, in the sense that it's going to be optimal given the data that the rule induces from the agent, okay? And under some conditions, one may think about this as being achieved or arising through some kind of an adaptive process, right? Where the designer is changing the allocation rule, the agent is varying her manipulation and response, the designer changes her allocation rule again, and under some conditions, this might converge to a fixed point. The other thing that one might be interested in is what we're going to call the optimal policy, which is the commitment solution or the Stackelberg solution. Okay, so this is going to be a case where the designer understands that the allocation rule is going to affect the agent's manipulation and picks an allocation rule that maximizes the designer's objective, accounting for that manipulation, understanding that while this is ex ante optimal, it may not be ex post optimal. In particular, it may not be a best response to the manipulation that it actually induces, but it is ex ante optimal, taking into account that changing the allocation rule will change the agent's manipulation. Okay, so in some sense, the commitment solution is really sort of severing the knot at this stage. Okay. Okay. So what we are interested in doing in this paper is comparing these two, specifically asking, how does the optimal policy, the commitment solution, compare to the fixed point policy? Okay, and what kinds of ex post distortions are induced by the optimal policy relative to the fixed point policy? So that's what we do. And just to get straight to the punchline, what we find is that in our model, the optimal policy is going to be, in a certain sense that we will make precise, flatter than the fixed point policy. Okay, or to put it another way, it's going to be less sensitive to the data that the agent is able to manipulate relative to the fixed point. Okay. So that's our answer to the comparison between the optimal policy and the fixed point policy. And in terms of what kinds of ex post distortions are induced, we're going to find that the optimal policy is going to commit itself to underutilizing data in a certain sense, right? Not using the data as much as one would want to if one were choosing the policy optimally in response to the data, okay, ex post. So, or to say this another way, the best response of the designer, if he was not accounting for the fact that changing the allocation rule will change the data, would be to actually use the data more, would be to put more weight on the data. Okay, so so that's where I'm headed. I want to sort of, most of the talk, given the short time frame, is just going to be focused on providing the model and the framework that generates the result and stating the result precisely and giving you a bit of intuition. But I want to point out sort of how we think about interpreting our result. So there are two ways in which one could think about our flattening the fixed point result. One of them is to think about settings in which the designer genuinely has commitment power. Okay, so I mentioned the example of Amazon, but you could also think about Google search, of course, or you could think about a government program that's targeting certain kinds of aid to agents who have certain kinds of observables here with commitment power. And so there we think of our result as being a positive result. This might describe exactly what they actually do. Or it could even be viewed as a normative prescriptive advice, which is if they've sort of converged somehow to a fixed point or are thinking about the fixed point, one should realize that the fixed point is not actually ex ante optimal for this designer and should actually flatten relative to the fixed point. There's another slightly more nuanced perspective, which is even if you have a market that let's say is a competitive market and therefore does not have a designer who has market power, for example, you might think about lots of small banks using credit scores in order to make lending decisions. I think Annie also mentioned this example in her talk earlier. Or you could think about lots of colleges using various test scores in order to make college admission decisions. So here we might think about the market sort of settling on an ex post optimal allocation because of the lack of market power. And then one could think about our result about flattening the fixed point as pointing to either what kinds of interventions would improve the accuracy of allocations. So this could be a government policy, for example, about banning the use of certain kinds of test scores or sort of saying how much they can be used. Or it could be another interpretation would be, what would happen if there was collusion in this market? Okay. So just a couple of words about related literature. I don't have time to go into this. I just want to point out sort of two papers. We're going to be building upon this framework that Alex and I in an earlier paper referred to as muddled information. So this is our 2019 paper, which itself builds upon a few other papers that I've listed over here. And then the other sort of very related papers, contemporaneous work by Ian Ball. This was his job market paper. And there's a substantial overlap in certain respects, and our main result has certain similarities. And then there are some things that we do differently than he does, and a different focus in his paper than we do. And I'm happy to sort of elaborate upon that offline. The other thing I do want to mention is that, of course, this idea of ex post distortions arising in ex ante optimal rules comes up in economics in lots of places. What we think is sort of novel here is the particular context in which this arises. And lastly, there's sort of this literature in computer science and machine learning that's referred to as strategic classification, which is the idea of using classification rules, typically in binary decision problems, accounting for the strategic behavior of agents. And so in a broad sense, we're also related to this literature, although the particular model and focus is somewhat different. Okay. Okay, so let me now jump into the model. So there's the setting in some sense very simple. There's an agent who has a two-dimensional type. Both dimensions are real numbers. And so I'm going to refer to the dimension eta as being the natural action and the dimension gamma as being the gaming ability. And this will become clear, the choice of the terminology should become clear on the next slide. There's a designer who wants to, who's going to pick an allocation, y, a real number, and wants to match the allocation to the agent's natural action, okay, and has a quadratic loss utility. So the designer is actually going to be picking an allocation rule, uppercase y, which is a function that depends upon some real number x that is going to be the data or the action that's generated by the agent. Okay. And we're using y and x here because we're going to be making a connection with OLS. So it's sort of useful to think about y as being the left-hand side and x as being the right-hand side. The agent is going to choose this data or action x based upon her type, her natural action and her gaming ability, eta and gamma, and the designer's allocation rule y in a manner that I will elaborate on the next slide. Okay. And so the expected loss for the designer, or the welfare loss for the designer, is simply the ex ante expectation of the quadratic loss mismatch between the allocation and the agent's natural action. Okay. So a very useful decomposition that's going to sort of guide a lot of our thinking about this is to decompose this welfare loss into two pieces. One of them is the information loss, and the other is the misallocation loss. Okay, so a little bit more specifically, because of the quadratic form, we can think about this loss as decomposed into two pieces. So the first piece is, how well are you able to estimate the natural action from the agent's data x? Okay, the quadratic loss associated with that aspect. And then the other piece is going to be, given the estimation, this expected value of eta given x, how well are you actually matching the allocation to that best estimate? Okay, so this we're going to call the misallocation loss given the estimation. Okay. And this decomposition is probably familiar to most of you, and it's simply coming from the quadratic form. Okay, so just reiterate, we can think about the overall welfare loss as having two pieces: information loss and misallocation loss. And it's really this trade-off between the two that is going to be central to our focus. Okay. So for tractability and for some other reasons that I will elaborate on if we have time for discussion at the end, we're going to focus on linear allocation policies for the designer. So the designer is going to choose an allocation rule that is simply going to be parameterized by two parameters, beta and beta naught. Okay, and it's a linear or more precisely affine allocation rule. And the constant beta naught is really not going to play much of a role in what we do. So really, the key thing to focus on is really essentially a one parameter family of rules that are parameterized by beta, which is the sensitivity of the allocation to the data x. Okay. We will see momentarily that you can also think about this as the strength of incentives that the designer provides to the agent. Okay, so to elaborate on why you can think about this as the strength of incentives, here it is. We're going to assume that the agent has a linear response function. So given the policy, specifically the policy sensitivity beta, the beta parameter, the agent of type eta gamma is going to choose an action in a linear form, which is given by this piece in blue. So what is this? First, notice that if I strip out the second part, then this would mean that in the absence of any incentives, the agent is just choosing action x equal to her natural action eta, and hence the terminology natural action. This is what the agent would do absent any incentives to manipulate. Okay, the parameter m is going to be a parameter that we're going to use. You can it's not going to play much of a role until we do comparative statics, so you can essentially put it in the background, but it's just going to be some positive parameter that's going to capture how easy it is for the agent to manipulate her data. Okay. You can also think about this as sort of a global parameter of stakes about how important the decision problem is for the agent. Gamma is gaming ability, as I suggested earlier. And the reason we call this gaming ability is that a higher gamma is going to make it more easy for the agent, or is going to provide greater incentive for the agent in order to manipulate the action. Okay. And gamma is heterogeneous across agents. It's private information of the agent. And notice that the beta term here is a global shifter for how much the agent manipulates. So the more the designer makes the allocation rules sensitive to the agent's data, all agents are going to be manipulating their actions by more. So we assume this linear response form directly because that's sort of what we want to really focus on. If one wanted to micro-found this, it's not hard. This linear response rule is linear response to the agent is going to be optimal given the linear policy for the designer if the agent's utility, for example, takes this form, which is the agent cares linearly about her allocation, and she has this quadratic cost of moving her action away from her natural action, scaled by her gaming ability, gamma. Okay, so the higher is your gamma, the cheaper it is for you to manipulate your action. And hence we think of this as gaming ability. Okay, so to summarize what the designer's decision problem is, she's given, there's an exogenous joint distribution over the agent's type, eta, natural action, and gamma, gaming ability. There's some means, there's some finite variances, there's some correlation between the two. The paper deals with generality in a couple of ways that I want to simplify for the purposes of the talk. And so I'm going to assume in the talk that the correlation is non-negative. Okay. That's natural in various contexts, although there are some other contexts in which one might want to think about negative correlation as well. For the talk, we're going to assume this correlation is non-negative. Okay. If you like, for some of it, you'll get the main ideas by even thinking about the correlation as being zero. Okay. The designer, therefore, is going to choose parameters beta star and beta star naught. This is going to give her the linear policy in order to minimize her expected quadratic loss, right? Minimize her welfare loss. And we can write this explicitly as just this minimization problem over here, which is simply, you want to get your allocation as close as possible to the agent's natural action. The allocation is given by this linear policy, and I've plugged in here that the agent's response takes the linear form that I mentioned on the previous slide. Okay. So this is an extremely simple and very natural model, we think, that has been used in various earlier work, but it is a complicated problem because this objective is actually quartic in beta. Okay, beta sort of enters over here, squared, and then you have quadratic loss, so that gives you the quartic. And for the purposes of the talk, in order to convey the intuitions transparently, I'm going to restrict attention to the designer only choosing non-negative sensitivities, beta. The paper also deals with the case where beta might be negative, and actually shows that at the optimum it won't be. Okay. And then lastly, I just want to stress that the comparison between what we're doing here and earlier work is that earlier work has essentially been looking at signaling game versions of this kind of a problem, whereas here we're thinking about the commitment solution, okay, the Stackelberg solution. Okay, so here's the basic logic. The key thing is that the following observation, which is whenever the designer increases the policy sensitivity beta, so makes the allocation more sensitive to the agent's data, she's actually going to increase her information loss about what she cares about, namely the agent's natural action, eta. Okay, and the basic intuition for this should be straightforward from the linear response function of the agent. Okay, so just stare at this for a second. Right? Think about the case where eta and gamma are uncorrelated for simplicity. the logic turns out to be more general. But if eta and gamma were uncorrelated, then increasing the policy sensitivity beta is simply like the agent's action is more determined by her type gamma, the gaming ability, rather than the dimension of her type eta, the natural action, right? If you like, another way to say this is it's sort of saying that more of the variance in X is going to come from the variance in gamma rather than from eta, which is what the designer really cares about. So this should suggest that making the policy more sensitive to the agent's action is actually going to reduce the amount of information that the action provides about what the designer actually cares about. Okay, I should say this is not information loss in the Blackwell sense. Okay, this is information loss in the sense of quadratic loss for the decision problem that the designer faces. Under some distributional conditions, for example, if we have normal distributions, this would also this would actually be a Blackwell ranking. Okay, so a way to just make this a little bit more precise, we could think about the following issue. Suppose that the agent's behavior corresponds to a policy beta. So the agent responds thinking that the designer is using policy sensitivity beta. Okay. Well, then the designer's optimal policy in response to that, the best response policy, would actually be to use not beta, but to use a different parameter, beta hat, a different sensitivity, beta hat, which is simply given by the OLS formula for the best linear estimator of the agent's type eta from the agent's action X. And we can do OLS here because of our linearity restrictions. Okay. So, and this is simply the OLS formula. I wonder if whoever is not on mute could just mute themselves.
Y le he dicho que si puede que busque los exámenes y que se lo cuente qué es lo que ha hecho mal, porque el niño necesita respuestas, ¿o no? Que haga lo que pueda.
So, yeah, again, if I think someone is not muted, if you could mute yourself, that would be great. So one can show that lower beta hat, right, corresponds to more information loss. Intuitively, if the designer wants to, in response to what the agent is doing, if the designer wants to put less weight on the agent's action, then this means that it must be that the designer is actually getting less information from the agent's action than if the designer wants to put more weight on it, right? That's intuitive, and one can show this formally, that a lower beta hat corresponds to more information loss, and moreover, beta hat is actually a decreasing function going from 1 to 0. Okay, and so this is just making a little bit more precise what I said earlier about if using a higher sensitivity beta makes the agent manipulate the data more, and this actually makes the data less informative for the designer's purposes. Okay, and so what is a fixed point policy? Now we can state this precisely. A fixed point policy is going to be a policy sensitivity that I'm going to denote by beta FB for fixed point, such that the optimal thing for the designer to do in response, the best response for the designer, would actually be to use the same sensitivity as she started with. Okay. This turned out to be unique because of the simplifications that I'm making in the talk. In the paper, it need not be unique. Okay. For the talk, I'll treat it as if it is, because it is under the assumptions. And you can think of this as a simultaneous move Nash equilibrium, where the designer and the agent are moving simultaneously. And crucial observation, at a fixed point, the misallocation loss must be 0. Because by definition, you're ex post optimally using the information. Okay. So given whatever information is available about the agent's natural action, the misallocation loss is 0. But however, the information loss may actually be very large because the agent's action may be mostly dependent upon her gaming ability and not upon her natural action.
Navin?
Okay.
5 minutes.
The picture, yes.
Okay.
Yeah. So I'm now ready to state the main result. So here it is. This is really the main theorem in the paper. So again, for the statement here, I'm assuming that the correlation is non-negative, which implies that there's going to be unique and a positive, unique positive fixed point, beta FP. Okay? So the optimal policy uses a sensitivity beta star that is strictly between 0 and the fixed point. And this is the sense in which we mean the optimal policy flattens the fixed point. It makes the allocation less sensitive, the agent's data, than the fixed point does. And then I also said that our other result was about underutilization of information, and that's made precise by the second part of the proposition, which says that, responds to the optimal policy beta star, what the designer would want to do ex post is to actually use a higher beta, right? That's the second statement over here. That is, the amount of information that the agent generates through her action in response to the optimal policy would actually mean that the designer, if she didn't have infinite power, would want to now make the allocation more sensitive in turn. Okay, so that's the main result. I don't have time to sort of go through much of the. Let me just point out that it's sort of easy to make a local argument, and that's basically what's in these first two bullets over here. You definitely sort of don't want to be using a sensitivity of 0, because if you 0, you're going to get a lot of information from the agent's action. Okay, in fact, a sensitivity of 0 would minimize the information loss, but would have lots of misallocation loss, and so you would want to increase your sensitivity from that. That's the first bullet. It's not hard to see that you actually want to decrease your sensitivity from the fixed point, because, as I said in the previous slide, the fixed point actually minimizes misallocation loss. It's ex post optimal. So what you care about then is just reducing information loss, which you can do by reducing the sensitivity, reducing how much you use the data. And so this means that there will be a local maximum that's between 0 and the fixed point. And the heart of the work is ensuring that this local maximum is in fact a global maximum. Okay. So I'm basically out of time. So we do some comparative statics. Let me just conclude by talking about a couple of sort of limitations and extensions. So one question is, our restriction to linear allocation rules, is that without loss? And the answer is typically it is with loss. Okay, so nonlinear allocation rules can typically do better than linear allocation rules. We make the restriction for a couple of reasons. One of them is we think that, for usual reasons, these are simple, they're canonical, they're frequently used, they're practical, but they're also sort of, we think, useful for intuition because they're straightforward to interpret. And we can talk about what it means to flatten or steepen, and what it means to under or overutilize data in a very easy way, which would be more complicated in a nonlinear model. Okay. And then there are easy extensions to sort of what if the designer cares about the manipulation cost directly? What if the designer sort of wants to induce the agent? If we think about the agent's gaming as being effort, productive effort, what if the designer cares about that? There are easy comparative statics that one could think about. So let me just conclude then by pointing out that one thing that we think that's very useful for further research is precisely what I alluded to, which is if you have nonlinear models or more general allocation problems, multi-dimensional allocation problems, high-dimensional ones, what are counterparts to our flattening or underutilization information? What would be good counterparts to those? We think is a very interesting area for future work.